Hi everybody, welcome back. We're continuing homework 8.2 and this is problem number 6. I'm going to add something to problem 6 here in just a second, but let me go ahead and read it, and then we'll make whatever additions we need to make. All right, so we have an 0.14 kilogram pine cone falling from rest. All right, right off the bat, let's go ahead and write down what we know about that. That is the initial velocity equals 0 meters per second. And it falls from a height of 16 meters to the ground, where it lands with a speed of 13 meters per second. Okay, so the final velocity equals 13 meters per second, and our distance d equals 16 meters. All right, you're probably used to writing that as delta x, in which case you would probably call that delta x is negative 16 meters. But just for now, let's just keep d a scalar quantity, and we'll worry about the direction a little bit later. Okay. So the assumption here is that that air resistance, which is mentioned in kind of part 1 of the problem right here, air resistance makes it hit the ground at a slower velocity, that is 13 meters per second, than it normally would hit the ground with. All right, and it tends to be true with pine cones. They have those little things that stick out and probably catch the wind. All right. And so we want to find out what the speed would be if there had been no air resistance. That's actually going to be pretty easy. That's going to be basically a kinematics problem. But the second part is what I'm going to add something to, and that is this. It says, did air resistance do positive work, negative work, or zero work? All right, that's where the direction is going to come into play, and we'll address that when we get to it. But I'm also going to add this. How much work? How much work by, oops, worky, didn't want to do that, work by, let me erase that, by air resistance. Work by air resistance. Okay, and we can figure that out, all right, and that's going to kind of tie into our work kinetic energy theorem right here. All right, so that's going to be the second part, or an addition to the second part that is part B of this problem. So, all right, let's go ahead and just attack part A and see if we can make some sense of that. By the way, give me just a second right here. I want to change the size of my my eraser so it's a little bit bigger. There we go. Sorry about that. Okay. So initial velocity to final velocity distance. What is the final speed if there had been no air resistance? So that really doesn't come into play for part 1. That is saying with air resistance. Okay, we want to find out without air resistance. So V final with no air resistance is really what we want to find right here. Okay, so V final, V initial, displacement. What's causing the acceleration? Well, we know gravity. All right, the acceleration is our 9.81 meters per second squared. All right, and we have our distance. I think we have a kinematics equation for that, and that being V final squared, I'll put that V final without air resistance squared, equals V initial squared plus 2 times our acceleration times our displacement, delta y, delta x, whatever you want to call it. I knew I was going to have to make my eraser bigger. Delta x, all right. Well, we said that our delta x is really our distance d, right? And we said that our acceleration is really gravity right here. So let's go ahead and substitute those in. We know those to be true. V final squared equals V initial squared, which by the way, is going to be 0, right? Because that's 0, plus 2 times our gravity, that's acceleration, times our distance d. All right, and our final equation for final velocity without air resistance is going to be the square root of all that, right? Because the original equation, I'm going to undo that and write a better, there we go, a better square root. The original equation had V final squared. We just want V final. All right, so that's going to be the square root of 2 times our gravity, it's 9.81 meters per second squared, times our distance d, which is 16 meters. All right, what do we get if we multiply all that out? I'm doing this in real time, so 2 times 9.81 times 16, and then I always take it to the 1/2 power to do the square root, and that is 17.7 meters per second. And that's exactly what we said. Well, not what we said, but what the question says. The answer is going to be 17.7 meters per second. All right, that was just kind of like a kinematics equation, right? No real big deal there. But let's now compare that to, let's talk about that in part B. After all, here's our tree, okay? And here's our pine cone in the tree right there, falling through that distance D. All right, and the question is, did it do positive work, negative work, or zero work? All right, well, remember, air resistance is very much like friction. In fact, it is a type of friction. All right, and friction always acts against the direction of motion. So that's a force of air resistance right there. And so if our direction of motion is downwards, and yet our air resistance is upwards, what is the angle between those two? Well, that's 180 degrees, right? If the work that is done equals a force times distance times a cosine of the angle phi between them, well, if that angle phi is 180 degrees, cosine of anything, the cosine of 180 degrees is always going to be -1. So it's going to be negative work. Air resistance, AR, equals negative work. Negative TIVE work, sorry. Okay, and that's because of the reason that I explained. You can write that down yourself, but it's because it is acting at a 180-degree opposite angle from the direction of motion. All right, now the thing that I added right here, how much work does air resistance do? All right, this is going to be a good application of our work kinetic energy theorem. Remember that we said that work that is done is the change in kinetic energy between two states. All right, what are the two states that we have? All right, well, we have the kinetic energy. Oh, by the way, change, of course, means difference in, right? We have the kinetic energy with air resistance, and we have the kinetic energy without air resistance right there. All right, that's really going to be what our work is. Now, if you have those in the wrong order, that's okay. You're going to come out with either a positive work or a negative work. We know that work is going to be negative, but the way that I set it up, I believe it's going to come out to be negative as well. All right. Well, let's write these out. What is kinetic energy? Kinetic energy is always 1/2 mv squared. All right, mass velocity with air resistance squared. All right, minus 1/2 mass of the pine cone times the velocity without air resistance squared. Okay, so that's going to be our change in kinetic energy, our difference in kinetic energy, and that will really represent the work that is done by air resistance to slow that down to prevent it from hitting the ground with a higher kinetic energy. All right, and by the way, if you're a skydiver, right, or a base jumper, you're counting on that kinetic energy by air, that work done by air, to slow your velocity such that your kinetic energy is less when you hit the ground. Otherwise, you're going to make a big mess. So let's go ahead and key all these in right here. So we got 1/2 mass of the pine cone. That's 0.14 kilograms, right? Times, what's the final velocity with air resistance? We were told all the way back up here that was 13 meters per second, right? So that's 13 meters per second, and that value is squared. Okay, and then from that we're going to subtract our 1/2 times, oops, I need another bracket there, I think. There we go. 1/2 times 0.14 kilograms, that's the mass of the pine cone, times what's our final velocity if there had been no air resistance. Well, we calculated that. That was 17.7 meters per second, and we're going to square that too, because that velocity is squared. So what do you get if you make that if you calculate that out, that difference in kinetic energy? What I get is that the work that is done by air resistance is going to be negative 10.1 joules. All right, so it hits the ground. It's not a very good box right there, is it? I'll do that again. It would normally hit the ground with a certain velocity. Due to air resistance, it hits the ground with a lesser velocity, and so air resistance has taken that amount of work out of the system to the tune of 10.1 joules. So that's our answer right there. I realize it wasn't put there in the original problem, but that's what we're shooting for because I added that to the problem right there. So 10.1 joules. Hope that makes sense. That's a good application of the work kinetic energy theorem. And if you have any questions, make sure you come and see me. Thanks for watching. I'll see you on the next one.